Okay, hello. Welcome everyone to the analysis section of the International Congress of Mathematicians. My name is Durgut Khansuragan. I will be a moderator for this section for this afternoon. Our speaker is Ronen Eldan from the Weizmann Institute of Science and Microsoft Research. Ronen will talk about revealing the simplicity of high-dimensional objects via pathwise analysis. Ronen, please, the floor is yours.
Okay, thank you so much for the introduction and the invitation to speak at the ICM. It's a great honor. So at the center of this talk are distributions that live in a high-dimensional setting, mainly Rn, where we think of n as being a big number, or in a discrete setting like the Boolean hypercube. One of the challenges dealing with high-dimensional distributions is the simple fact that the number of configurations of a system increases exponentially with the dimension. Sometimes this is referred to as the curse of dimensionality. Due to this richness or this diversity, one might expect that such distributions will be essentially intractable. However, as it turns out, in many examples of interest, there are ways to tame this behavior. And the main driving force that allows us to do this is encompassed in the relatively recent theory of phenomena in high dimensions. What this theory shows is that often high-dimensional objects, perhaps counterintuitively, actually behave surprisingly well. And in many cases of interest, the high-dimensional object has an underlying simple structure that, when viewed correctly, basically compensates for the fact that it's high-dimensional. Some expressions of being well-behaved are in this list. And in this talk, we're going to get a glimpse into some of these features and how this works. And our main goal will be to present a new technique, which has proven rather useful in proving that certain high-dimensional objects are well-behaved. So what we'll start with is what is sometimes referred to as dimension-free behavior. And I think the best place to start when talking about this kind of behavior is the so-called Gaussian isoperimetric inequality. So let's dive in. We're talking about the space Rn here, equipped with the standard Gaussian measure. This is its density. And in isoperimetric inequalities, we deal with surface areas. And in order to talk about the surface area of a set with respect to a measure, which is not the usual Lebesgue measure, one of the best things to do is to define the so-called epsilon extension or thickening of a set. So for set A, I define that its epsilon extension to be simply all of the points whose distance from A is at most epsilon. And what an isoperimetric inequality will do is, from among the sets that have some prescribed measure, try to find the sets whose epsilon extensions are minimal. And so the Gaussian isoperimetric inequality, which was proven by Borel and independently Sudakov and Cyrilson in the 70s, states that the extremal sets are half spaces. To be more precise, for any set A, if I take a set H, which is a set of this form, so it's just defined by some affine inequality, some half space in our space, and I take H so that the measures of A and H are the same, then I consider the measure of the epsilon extensions of both A and H, we will always have that H minimizes the measure of the epsilon extension. When epsilon is small, you can think of this as some kind of notion of surface area. Now, one of the main points here is that this inequality is dimension-free. So first of all, note that the extremal sets only depend on one direction in space. This set is, essentially one-dimensional in a sense. Now, since the Gaussian measure is both rotationally invariant and it's a product measure, it's pretty easy to see that the quantity here on the right-hand side does not depend on anything except for the value of epsilon and the measure of the set A. It does not depend on the dimension. So in this sense, the inequality is dimension-free, because if I write the expression for what this quantity is equal to, it will not depend on the dimension. Now, this inequality is useful for many reasons. One reason is that it implies strong concentration properties. For example, if I take a one Lipschitz function from Rn to R, and I use this inequality, I just apply it on the level sets of this function f. What we can conclude is the following. We can conclude that the probability, if I take a random Gaussian point x, plug it into the function f, and look at this random variable f of x, the probability for it to deviate from its median by more than some quantity t is at most this e to the minus t squared, which means it has sub-Gaussian tails. So Lipschitz functions are very concentrated around their mean, and it's actually not very hard to check that the functions which maximize the extremal cases for this inequality are linear Lipschitz functions, which basically, again, are one-dimensional. So also this inequality obviously does not have the dimension inside it. It's independent of dimension, and it's hard to overstate the number of different applications this inequality has. It's basically the driving force behind many results in, for example, statistical learning theory, dimension reduction, and other things. Okay, so these bounds are relevant to Gaussian space, which we kind of want to think about as a model space for high-dimensional distributions. And it turns out that, well, many other a priori more complicated distributions tend to behave in a similar way. So let's give an example. So for product distributions, for example, if you try to find the eigenfunctions of the Laplace-Beltrami operator, it's not hard to see that they will be separable with respect to coordinates, which will imply also that you have some dimension-free concentration. But it turns out that there are more complicated families of distributions where you also observe these kind of phenomena. And in this talk, we'll focus mainly on two cases. The first case is so-called log concave distributions. So this is just some kind of generalization of the Gaussian measure. It's measures on Rn whose density is of the form e to the minus some convex function. So the Gaussian measure is a special case, but for example, also the uniform measure on a compact convex set is another special case. And the other family we'll consider is Gibbs distributions, which have well-behaved Hamiltonians. So let's start with log concave distributions. And here we'll mainly consider one conjecture called the Cannon-Lovász-Simonovitz conjecture from 1995. So let's try to understand what this conjecture means. For a probability measure mu on Rn, we'll define its concentration coefficient as the supremum of over all test functions of the ratio between the variance of the test function with respect to the measure and the expectation of the gradient square of this function. So if this coefficient is small, it basically means that any function that does not locally vary too much, typically its gradients are pretty small. It does not also globally vary too much. This numerator is basically corresponds to the variation, the global variation, and the denominator is how much it changes locally. And what we'll want to do is we want to compare this with the linear concentration coefficient, which is exactly the same thing, only we're only able to take linear functions here over the supremum. So what the conjecture says is if we have a log concave measure, just a measure with a convex potential, then the concentration up to a constant, which does not depend on the dimension, will be bounded by the linear concentration. Now, if this is true, this kind of says that the concentration coefficient is dictated by the behavior of one-dimensional object. Well, linear functions we can just think of as one-dimensional objects because they only depend on one direction. So the concentration will be dictated by the concentration of the marginals, one-dimensional marginals of the measure. This conjecture has several implications. One famous one is the so-called Bourgain's slicing problem. It was established by Bol and Huyen and by myself and Klartag, that one implies the other, and the slicing conjecture has far-reaching implications in convex geometry, which I'm not going to touch upon, but I highly recommend the talk by Keith Ball in the ICM 2 days ago, if you who gives many such connections. The conjecture was actually motivated by its computational applications. It implies direct bounds on how efficiently one can sample from some measure, from such measure, using Monte Carlo methods, and it also has implications to algorithmic volume estimation, PCA, convex optimization, etc. Okay, so this was the example that has to do with log concave measures, and now I want to consider a slightly different example, which has to do with pure state decompositions for Gibbs measures. So this slide is going to be a bit vague, but another class of distributions which turn out to be well-behaved come from statistical mechanics, given a measure on this discrete hypercube this time, defined by e to the minus beta times some Hamiltonian h. This Hamiltonian could be any function, but let's think about it as some simple function, where by simple we might mean that it's a low-degree polynomial, for example. In many cases, we observe the following phenomenon. We observe that when beta, which is sometimes called the inverse temperature, is small, then the effect of H is not too significant, and the model is in some kind of high temperature regime, which basically refers to the fact that it looks kind of like a product measure. So typical correlations between coordinates are negligible for most pairs of coordinates. And if we take a larger beta, this is not true anymore. We observe non-negligible correlations between different coordinates. But in this case, in many cases of interest, we still have some very interesting structure. Namely, the measure can be expressed as a mixture. We can write it as some kind of convex combination with the number of components not being too big, such that each of these measures individually is in some sense close to a product measure. So it's not a product measure by itself, but it can be decomposed into a small number of product-like measures. And in this case, the analysis boils down. In this case, basically, there's a global structure, which is just understanding what those measures are. And the local structure is much simpler. So there is an underlying simple structure to the measure, and we'll touch upon this later more concretely. Okay, so as I mentioned, in this talk we'll introduce an approach which should help us prove the sort of things we have just seen. And the approach will be based on pathwise analysis and stochastic calculus. But as a prelude, I'd like to explain a related approach, sometimes called Martingale techniques, and I'll explain it through a simple example. So here's the setting. We consider a function phi from the set of n-bit strings, two real numbers, which I assume to be a one Lipschitz function with respect to the Hamming metric. So if I change one bit in this string, the value of the function changes by at most 1. And now let x be a uniform point in this discrete hypercube. And what we want to derive is concentration bounds on phi of x. We want to say that phi of x does not deviate from its expectation or median by too much. We'll do this by the main idea will be to consider the following process. So this is a stochastic process indexed by discrete time I. At every time I, what we look at is the expectation of the value of phi at the point x, conditioned on all of the information that we have revealed up to time I. So we look at the expectation of phi of x. At time 0, we just have the expectation of phi. At time 1, we have the expectation of phi conditional on knowing the first coordinate, then conditional on knowing the second coordinate, etc., etc. So we reveal the value of phi x coordinate by coordinate. Now, it's not hard to see, and this is just the law of total expectation, that this process has a very nice property that if I condition on all the information up to time I, and I look at the difference between the process at time I plus 1 and the process at time I, those differences are unbiased. They have expectation 0. These sort of processes are called martingales. It's just processes such that their conditional increments are unbiased. It's also easily seen that when I reveal one more bit of information, the expected value of the function can change by at most 1. This is an immediate consequence of the fact that the function is one Lipschitz. So the differences of this process are bounded. Now, we have a process which is both a martingale, and the differences are at most 1. Let's suppose for a second that the differences would be exactly equal to 1. Then this process would actually have a name. It would be called the simple random walk. That's the only process which is unbiased and has differences exactly 1. So the process we are looking at is in some sense dominated by the simple random walk. Now, it's well known that the simple random walk, in a sense, converges to a Gaussian, and it has very nice sub-Gaussian tail behaviors. And we have something called the Zuma's inequality, which basically says that if we have an inequality here rather than an equality, we will still have the same type of concentration bounds, and we can basically derive this type of deviation inequality. Now, what we did here on a meta level is we took something which is high dimensional, this object, this function phi, and instead of analyzing a high dimensional object, we associated to it a process which actually lives in one dimension. Those mi's are scalar, but we kind of traded the high dimensionality by introducing a notion of time to the process. And then we kind of analyzed what the process does in an iterative manner. And this kind of meta philosophy is what we are going to consider in our main technique, which I'm now going to move to. But the main difference will be is that we are going to reveal our randomness rather than bit by bit, like in the example we just saw. We're going to try to reveal the random bits infinitesimally, in a sense. And if we do that, this will give us new tools at our disposal, which will allow us, for example, to differentiate with respect to the randomness. So let's try to give an overview of what the meta technique looks like. So suppose we have some measure mu, and we want to sample from it. The measure mu is on some space, say Rn, the discrete hypercube, but really pick your favorite space. The way we'll sample from it is we will use our source of randomness as we'll use a Brownian motion as our source of randomness. So we take a standard Brownian motion B in R to the K for any K, but think of B as being in Rn as well here. And what we want is we want to find the mapping G, which takes as an input the path of a Brownian motion. So the input is not just one point, it's the whole path of the Brownian motion between time 0 and time infinity. And the output of this function is a point x in our space. And what we want is that G will push forward the measure, the canonical measure on the space of paths to the measure mu. So we wanted to have this property that if we take B and plug it into this mapping G, the output will have the prescribed distribution that we want. Okay, so given mu, we want to find a GU that has this property. And just as a simple example, if mu is the standard Gaussian measure on Rn, we can just take G of B to be the Brownian motion evaluated at time 1, which we know has the distribution of a Gaussian. So this is kind of abstract, but the reason this will be useful is that now we have introduced the time axis. And once we did this, we can actually condition on everything that happened up to some time t, and we can differentiate things. So it's going to be useful to consider the measures obtained by conditioning basically the measure of G of B, which is a measure on omega, which is obtained by conditioning on all the information that we have up to some time t. So this is a family of measures. It's a random family. At time 0, we condition on nothing, so we simply have the measure mu. At time infinity, we already know what the point is, so we just have a Dirac measure. And in between, we have some kind of interpolation between the measure mu and some Dirac measure. So think about a process that keeps focusing, zooming in until it gets to one point. Okay, now let's talk a little bit about what one might do with this. So suppose we have some test function phi on our space, and we want to show that it's concentrated. So a very natural thing to consider is a process m of t, which is completely analogous to what we had 2 slides ago, which is the expectation of phi at the point we are going to sample, conditioned on all the information we have up to time t. Okay, so in 2 slides ago, we conditioned on those random bits that we revealed. Here we condition on the path of the Brownian motion up to time t. Now, one thing we can do is differentiate this process with respect to time. And it turns out that there is some kind of chain rule here saying that the time derivative of mt will correspond to the instantaneous change of this Brownian motion bt, and it's always going to be in some certain direction. So somehow at any point in time, to understand how mt changes, We only care about the projection of BT on one direction in space. And this vector VT will kind of help us reveal the directions which are important in our analysis. Now, if we care, say, about the variance of the test function, a very general fact called Ito's isometry will tell us that this amounts, in a sense, to the sum of squares of the instantaneous change in the Martingale MT, sometimes called quadratic variation. So the variance of this function phi is by definition the variance of this Martingale, this process between time 0 and time infinity. This is the expected square of something, and we can think about it as the sum of expectations of the square differences, which, since they are uncorrelated, these two things will just be equal. And in turn, the analysis of this will just boil down to understanding how big this vector VT is, which basically determines, we can think about this VT as the differential of this process MT. So we just want to say that the differential is kind of small. Okay, so far this has been kind of abstract, and what I want to do now is consider a specific manifestation of this meta technique. Namely, I want to find an actual embedding between Brownian motion and some prescribed measure mu. And I will do it by first considering a discrete version of a process, sometimes called stochastic localization. So this is a process that takes a Brownian motion and outputs a point. The discrete version will look like this. Again, we have some prescribed probability measure mu, this time specifically on Rn, and we'll iteratively construct a sequence of measure mu I by the following procedure. So let's take an infinite sequence of independent standard Gaussian random vectors in Rn and fix some small epsilon. What we'll do is the following. Given that we've already constructed the measure mu I, the next measure in the sequence mu sub I plus 1 will be constructed by taking the measure mu I and multiplying its density by a linear function. This is just a linear function of x here. The gradient of this linear function will be random. So it will just be a Gaussian, which is independent from the past, times some small epsilon. And this affine coefficient, it is the center of mass of the measure. So this thing we're multiplying by is a linear function which is equal to 1 at the center of mass. This is the unique way to ensure that multiplying by this factor does not change basically the mass of the entire measure. So if we had a probability measure at time I, we will still have a probability measure at time I plus 1. Well, given that this factor is non-negative, of course. As long as it's non-negative, we will have a sequence of probability measures by this procedure, and we basically take the product of those linear functions with random gradients. Now here epsilon is finite. It turns out there is a way to actually take epsilon to 0 and basically multiply by linear functions with random slopes. This gives rise to some kind of system of stochastic differential equations where the Gaussians we had before will now be replaced by a Brownian motion which is driving the process. I don't want to spend too much time on how to do this exactly, but there is a good way to do this. And in fact, we'll consider a family of such processes we can take those differentials of the Brownian motion and multiply them by any driving matrix valued process HT, which will give rise to several ways to do this localization. Okay, so let's now review some basic properties of this process. So first of all, by the fact that we took this center of mass as an additive coefficient, we have that this process is a process of probability measures. At time 0, we have the original measure, and at any point in time, we have a different probability measure. Now, this process will be a Martingale. So as above, in expectation, the measure of a given set A will not change. The increments will be unbiased. This is just due to the fact that we are multiplying by an unbiased quantity. Now, we're not going to see this immediately, but this process that we get, mu t, is some kind of interpolation between the original measure mu at time 0 and a Dirac delta measure at time infinity. So we start with the original measure and it kind of localizes in space until it gets to one point. And by this Martingale property, it's clear that the point that we get to eventually is just a point that has the law mu. So it can be seen as a sampling procedure as before. Now, again, by this Martingale property, we immediately get that for every time t, the process gives rise to a decomposition of the measure mu. We can present it as the expectation of the measure mu t. The expectation is over the randomness coming from the process, so it gives rise to these mixtures. Okay, so let's now review some features of this process that will basically help us make high-dimensional measures more tractable and prove inequalities and facts about them. So recall again that suppose we have some test function phi, and we want to show that it's concentrated. We can associate with phi this Martingale that we considered before, and this Martingale will always satisfy that its derivative is some vector vt times the differential of the Brownian motion, and we saw that the variance is just the integral of vt squared. Now, in this specific process, this vector valued process vt actually becomes quite tractable. So the differential, by definition, the differential of this measure valued process is the same process, but we always multiply by this linear factor. So whenever we take the time derivative, this linear factor in x kind of pops out of the equation. And if we just plug this fact into the definition of MT, what we will get is that the differential of this Martingale is the vector vt, which is just some kind of spatial moment of my measure mu t. So time derivatives of this process correspond to moments in space. And we can actually differentiate again and again, and we will get some kind of moment generating property, which will make the differentials of this process very tractable. We have very simple expressions for these, for the way that the Martingale changes in time, which will facilitate its analysis. Now, another nice feature is the following. So a calculation that uses something called Ito's formula shows us that at any time t, the measure mu t actually has its density with respect to mu actually has a pretty simple form. It is always the exponent of some quadratic expression. So this thing, you can just think about it as the density of some Gaussian. And well, the the quadratic term in this quadratic expression will just be deterministic, and all of the randomness will basically be incorporated inside those processes BT and AT. So even though, you know, we had an infinite system of equations basically for every point X, we keep multiplying by those infinitesimal linear functions. And what we see is that at any time t, effectively, we've just multiplied our measure by some kind of Gaussian density. And the reason that a Gaussian term pops up, shows up, but when you keep multiplying by linear functions, is actually very simple, at least the intuition behind that reason. So suppose we're in one dimension and we take some function and we multiply it by either the function 1 plus epsilon x for small epsilon, or the function 1 minus epsilon x. So we multiply it by a linear function with either a small positive slope or a small negative slope. Of course, by the law of large numbers, most of these multiplications will cancel out each other. Okay, suppose that, you know, those plus and minuses are chosen according to independent Bernoulli random variables. So most will be cancellations, and each cancellation will contribute a term that looks like 1 plus epsilon x times 1 minus epsilon x, which is equal to 1 minus epsilon square x squared. So each cancellation will contribute a quadratic expression. And if we do 1 over epsilon square iterations like this, then we have basically multiplied by this function to the power 1 over epsilon square, which looks like e to the minus x squared. Okay, so this kind of makes it clear that a Gaussian term should arise. Now, this turns out to be very useful because it takes a measure which is not a Gaussian, it introduces a Gaussian term, which will later allow us to use several properties and inequalities about the Gaussian for our original measure. So it will kind of decompose our measure to components which have a Gaussian-like behavior. Okay, the third feature that I want to present is the following. So if I consider the centroid of our measure, CT, so this is a vector valued process, and I try to differentiate it and see what its evolution looks like, it's just a straightforward calculation that it moves faster in directions where the covariance matrix of the measure mu t is larger. So it kind of has a tendency to explore the directions where the measure has large covariance. And if we just plug this into the law of total variance, what we'll get is that in expectation, if I look at the covariance measure of the covariance matrix of this measure mu t along the process, so this is a matrix valued process, and I try to analyze it, I see that in expectation, it satisfies this Riccati type equations. It decreases in a rate that's proportional to the square of this matrix. So whenever I have a direction with large covariance, it's going to quickly collapse to something much smaller. And this is useful because in the case of Gibbs measure, for example, it causes my measure to collapse into a pure state. Okay, so let me finish with very quickly reviewing a sample of some of the applications of this method. So in the last 10 years, that's my main project, was basically trying to prove things using this meta technique. And some of the applications are functional inequalities in Gaussian space, applications to high-dimensional convexity, in particular the KLS conjecture, mean field theorems and sufficient conditions for pure state decompositions, concentration and mixing bounds for discrete measures, with applications to sampling bounds for Markov chains, and also applications to the theory of Boolean functions. Let's zoom in on some, really quickly review some specific applications of this. So first of all, the KLS conjecture that I mentioned above, that talks about the concentration of log concave measures on Rn. Just to remind you, it asserts that the concentration of a measure is up to a constant determined by the concentration of linear functions. So this stochastic localization process was first introduced in this paper, where it was shown that instead of reducing it to linear functions, you can actually reduce it to a slightly larger family of quadratic functions. So this laid out some tools for the analysis of concentration on low concave measures. And later on, a series of papers, first by Lian Vimpala, then Yuanzi Chen, and very recently Klartag and Lehek, basically relied on this process to derive concrete bounds for the concentration of low concave measures. And it is now known that there is a polylogarithmic bound for the concentration. So not quite a constant, but nearly a constant. And this implies corresponding bounds on Bourgain's hyperplane conjecture. The second application is for some kind of L1 version of hypercontractivity. So a classical result in Gaussian space asserts the following. If I consider the Ornstein-Uhlenbeck semigroup, which is just basically the heat semigroup in Gaussian space, it has a very nice smoothing property formulated as follows. If I take any function f, which is in LP, and I apply a little bit of this smoothing operator, Ornstein-Uhlenbeck operator, pt to the function f, then this smooth function will already be in LQ for q bigger than p, and there is actually a quantitative estimate for this. So this is lower or equal with coefficient 1. Now, for the case for functions in L1, no quantitative smoothing effect was known, and it was conjectured by Talleyrand that if you have a function in L1, then after applying PT, it will satisfy an improved weak L1 inequality. So without this little o here, it's just, the usual Markov inequality. But if you smooth it out a bit, you already get some little o, which is some kind of quantitative improvement. The third application is, or family of applications, are structure theorems which try to find sufficient conditions for pure state decompositions. So as an example, if you have an Hamiltonian in Rn, which has the property that its set of gradients cannot be correlated with a Gaussian direction. So the set of gradients has a small Gaussian width. Then I can write this measure as a decomposition into a family of measures, such that if I go to the components of the decomposition, I do not lose much entropy. And each individual component is typically close to a product measure. Finally, there are some applications to sufficient conditions for concentration on the discrete hypercube. So we can define a concentration coefficient in a similar way to what we had in Rn. And you can use this method to derive several sufficient conditions, which in turn imply fast mixing for Markov chains, which help us sample from these measures. Okay, so let me just finish by again showing the slide which lists some of the other applications. Yeah, thank you so much for your attention.